Welcome into the class of topology, and in some previous videos we are continuing towards the chapter of compactness, and in previous video we have discussed something about local compactness, and in this video once again I'll be continuing with the same topic, local compactness. In the previous video we have shown that closed subspace of a locally compact space is locally compact, but every subspace of a locally compact space need not be locally compact. That means local compactness is not a hereditary property. So this is the starting of the day today. Local compactness is not hereditary property. So if we are saying that it is not hereditary property, then we will have to give some example where the space is locally compact, but some subspace we will find that will not be locally compact, to show that it is not a hereditary property. And the example is very trivial. You look into the R along with the usual topology, the set of real numbers with usual topology, then it is locally compact space. Why it is locally compact? For any x belonging to R, for any real number, you are having this open neighborhood x minus epsilon, x plus epsilon of x, and its closure is, suppose it is M, then what is closure of M? It is the closed interval x minus epsilon, x plus epsilon, and we know that this closed interval, that closed set x minus epsilon, x plus epsilon is compact. That means for every x belonging to R, you are having an open neighborhood of x whose closure is compact, so this Ru is locally compact. But if we talk about its subspace Q and UQ, UQ means the relative topology where all the open sets are the open sets of U intersected with Q. So this is the topology defined on Q, subspace topology. This is not locally compact. Why it is not locally compact? Because if you take X in Q, what type of neighborhoods this point X will have? The neighborhoods will be of the type X minus epsilon, X plus epsilon, but intersected with Q. Actually, we will see the neighborhood in R and then we will intersect with Q to find the relative neighborhood in the subspace Q. And let us talk about its closure now. So closure M bar is x minus epsilon, x plus epsilon intersected with Q and bar. And we know that A intersection B bar is A bar intersection B bar. So you can have it like this. And what is the closure of this open interval? Closure of this open interval, we know that it is the closed interval x minus epsilon, x plus epsilon, and intersected with Q. Now, the problem is, how can it be compact? If it is compact, the space will become locally compact. But how can it be compact? It cannot be compact. The reason being that open sets in UQ, open sets in UQ will have only rational numbers, and such open sets cannot cover this M bar. Why cannot cover? Because this interval is having, and here once again, this Q bar is R, this Q bar is R, and this closed interval intersected with R is the closed interval itself. So this M bar is containing real numbers also, irrational numbers also. These irrational numbers will not be covered by the open sets in UQ, because UQ contains open sets having only rational numbers. So irrational points here will not be covered, and if we are not having any open cover, how can we talk about the finite subcover? So it is not compact. So here we are having a locally compact space Ru and its subspace QUQ, which is not locally compact. So we have shown that a locally compact space and its subspace need not be locally compact. So local compactness is not a hereditary property. And then I am moving towards another theorem related to local compactness, and the statement of the theorem is open continuous image of a locally compact space is locally compact. So this is the next theorem in local compactness. So what we are required to do here, we will take one locally compact space X tau. So let X tau be a locally compact topological space. Let F from X tau to another topological space Y rho be open, continuous, and onto we will have to, because we need image. So image will be used, the word image will only be used if it is onto. So this space X tau, this is given to be locally compact, and we will show that this Y rho is also locally compact, because now it is open continuous image of a locally compact space, and we have to prove that open continuous image of a locally compact space is locally compact. So we will have to prove that this Y rho is also locally compact. For that, we will take an arbitrary point small y from this Y, and we will find an open neighborhood of that particular point Y whose closure will be compact, and that will make Y rho a locally compact space. For that, I am going to start with let Y be a point of Y. Since it is onto, we are talking about the image, since it is onto, so for this Y in this capital Y, there will be some x in small x, capital X, such that fx is equal to y. So therefore, there exists x in capital X such that f of x is equal to y. Now this x is in capital X. That means this x is a point of this topological space X tau, which is locally compact. And if it is a point of a locally compact space, then definitely there will be a neighborhood, an open neighborhood of this point X whose closure will be compact. So therefore, there exists an open neighborhood M of X whose closure F bar is compact. Here I have used the definition of local compactness of the topological space X tau. So M bar is compact. Now M is open neighborhood of X. Concentrate on this. Open neighborhood M of X. And your map is open. F is open. So this means f of M will be open neighborhood of f of x, and f of x is y. So that means your f of M is an open neighborhood of y because f is open. Also your f is continuous. So this means f of m bar is a subset of f of m whole bar. This is from your chapter of continuity. So f is continuous, so f of m bar is a subset of f of m bar. Once again, f is open and continuous. This means f is also closed. F is also closed, because if a map is open as well as continuous, then it is always closed. So it is also closed. F is closed. Your m bar is closed, you know. Closure of a set is always closed. M bar is closed and f is also closed, means your f of m bar is closed. F of m bar is closed. And for a closed set, its closure will be equal to the set itself. So this means f of m bar, it is a closed set, so its closure will be same as the set f of m bar. So I need space now to write more. So f of m bar is equal to f of m bar. Now look at this and this. Here your f of m bar is equal to this, and here your f of m bar is a subset of this. So that means this is a subset of this. So combining these two, you can write f of m bar is a subset of f of m bar. Once again, you know that m is always a subset of m bar without any doubt. Every set is a subset of its closure. Taking f on both sides, your f of m is a subset of f of m bar. And you know that if a is a subset of b, then a bar is also subset of b bar. So here this is your a, this is your b, a is a subset of b. That means a bar is a subset of b bar. So your f of m bar is a subset of f of m bar. But f of m bar is equal to f of m bar. So it is equal to f of m bar. Now your m bar is given to be compact. Your m bar is compact because m was the neighborhood of the point x in the locally compact space x top. So m was the neighborhood of the point x whose closure m bar is compact. We have written it here that m bar is compact. So m bar is compact and your function f is continuous. And your function f is continuous. We know that continuous image of a compact set is compact. So m bar is compact and f is continuous. So f of m bar, that means continuous image of a compact set, is compact. So this means your f of m bar is compact. But f of m bar is equal to this f of m whole bar. So you can say that fm whole bar is compact. Now look back. What is your f of m? Your f of m is open neighborhood of y. You have taken this point y from the topological space y rho. And this point y was arbitrary. And for this arbitrary point, you are having an open neighborhood f of m whose closure is compact. And that means your topological space y rho is locally compact, and that was required to be proved, that open continuous image of a locally compact space is locally compact. So here we finish with the topic of local compactness, and in the next video we will move ahead with next topic, Till then, thank you. Thank you once again.